Hello and welcome to the measurement of maximum pressure and flow rate of an electric hydraulic pump. My name is Trine Mullins.
I'm Robert Dietrich.
I'm Nick Davis.
I'm Isaac Zager.
We're going to talk about first a little outline of our project. The outcome of it was to get an accurate measurement of the flow rate and maximum pressure of the hydraulic pump used by the front-end loader senior design group, and also get the uncertainties for those measurements.
Here is our roadmap to kind of help us along to complete this project in a timely manner. The first thing we conducted and completed was the mini report. The cylinders were not in our possession at the time until about a few weeks ago, so that's when we conducted these tests. Once they were delivered, we obtained the relief valve pressure and calculated the uncertainties, as Nick previously stated. We also had to design a testing setup to figure out the flow rate of the hydraulic pump using the cylinders, because there was two of them and they were not going at the same flow at the time. We then executed these testing methods, gathered data, converted the video into Excel data, and then completed this presentation.
So the reason behind this experiment was to find the flow rate and maximum allowable pressure for a hydraulic system for the front-end loader senior design project. We needed to find the flow rate of a donated pump, and we needed to know the lift speed of the bucket for the front-end loader and the lift capacity.
So some of the background and objective of this project, we need these measurements to determine the required lifting rate of the loader. Our requirements state we need to have a ½ foot per second with no load. We also have a lift capacity requirement of at least 500 pounds. There have not been any tests run to prove the speed and the flow rate of the donated pump prior to this project, and there's not much information on it as it was donated and it's an older model. The flow rate of the pump will provide information to conclude the lifting speed of the loader arms, and the pressure rating will confirm that the load capacity is possible, as well as not overloading the safety of our cylinders or hoses.
So some of the equipment that was needed to run our flow rate experiment was a cell phone with a recording capability, a tape measure to measure the distance traveled of the hydraulic cylinders, the hydraulic pump itself and the controls needed to run it, the hydraulic cylinders and then their known dimensions from manufacturer specifications, a 1/4 inch MPT pressure gauge to read the maximum pressure, clevis pins to help align the two hydraulic cylinders during our testing, the 2x4 blocks that were set up on top of each other to align the phone and get it at a proper height to be able to see the tape measure as they travel past it, a C-clamp to help in fixturing level to ensure that the phone was as good as possible horizontal with the hydraulic cylinders, a jam nut, and then a table used to put the fixture on top of.
So here's an overview of our measurement system. Here you can see the tape measure going in between the cylinder arms, and then you can see these wood block fixtures to hold the phone, then the level to make sure that the phone is parallel to the plane of the measuring tape, and then the clevis pins are here in the rear of the cylinders and at the end of the arms, and then you can see the hoses going from the cylinders to the rest of the hydraulic system.
As you can further see, the clevis pin here that Robert previously mentioned helps align those cylinders. There's also one up in front. On this picture on the left, we have measured the height at which the phone camera was at. It was at a distance that you could see the tape measure with ease, as well as the parallax method, which is basically looking at the same object at a different distance and angle.
So just further description of the test setup. On the left-hand photo, you can see how the level was rested on top of the phone to try to get as horizontal in comparison to the arms extending. On the right-hand photo, you can see how the clevis bar ran through the tie rod ends of the hydraulic cylinders, and this allowed for us to get at the very front of the clevis pin the starting point where we would reference where we started and where we ended with the travel of the arms. These arms were basically procedure-wise, Trine would activate the switch and the arms would extend out. We would start the recording before the arms moved and end it after. And then I believe here is a little bit of data analysis on the cylinder. As I said before, start and end points were recorded, time was taken, and then velocity was calculated using distance over time. And then from that, using the volumetric flow rate is the area times the velocity, we were able to determine the flow rate of the system. And here is a little video showing how we acquired the data. Stop.
So the pressure measurement system required a little bit different setup. So a little bit of procedure was installing a 1/4 inch NPT pressure gauge at the auxiliary C2 extend port as shown in the figure. You see the X, the pressure gauge is denoted in blue, and it's shown in the picture physically on the pump. So once that's installed, we fully extend the cylinder and run the pump at the deadhead against the relief valve, which is shown here in red. And while that's running against the relief valve, we can record the gauge reading.
So the mathematical theory behind calculating the volumetric flow rate is fairly simple. You take the area perpendicular to the motion of the cylinder arms inside of the piston and just multiply that times the linear velocity of the cylinder arms.
Some assumptions we had included when running these experiments. Both cylinders flow at the same rate, which we know they did not at the beginning until we designed a test setup that helped kind of eliminate that. The camera is exactly perpendicular to the measuring point. There is no pressure fluctuation in the pump during operation. We neglect the tape measure shift, as you may have noticed in the video Nick showed that it moved slightly. We are assuming constant pressure of the closed system for when measuring the pressure device. And we are neglecting the parallax that I previously mentioned.
So let's lead into some results of our measurements. Like I said, we recorded from a frame of reference on the front of that clevis pin the starting and end point of the cylinder travel. From that, we're able to get a delta and the position shift. And then from the video recording, we're able to pinpoint where the start and end of the movement occurred. And with that, we were able to calculate the inch per second velocity of the hydraulic cylinder pistons. And then using the equation that Robert talked about, our volumetric flow rate, we were able to calculate with the bore diameter of the hydraulic cylinder and the velocity, the flow rate of the hydraulic pump. These tests were repeated on an extension and retraction 4 times. And then from that, we were able to gather an averaged flow rate of our system. Moving on to the maximum pressure result, doing that deadheaded operation of the cylinder, we were able to find, based off of the gauge, that the maximum pressure was 2200 psi. Leading into the uncertainty of the flow rate calculation, denoted by the picture on the right-hand side, and also on the left-hand side we had uncertainties in our measuring tape from the resolution, the bore diameter of the hydraulic cylinder from the manufacturing specifications, and then from the resolution of the video recording based off of 30 frames per second, we were able to determine its uncertainty. So as seen in the calculation to the right-hand side, we were able to propagate the uncertainty through our flow rate calculation and determine that we had about plus or minus 0.005 gallons per minute of error. Leading into our maximum pressure uncertainty, we had a gauge resolution uncertainty, and then an operating full-scale output resolution uncertainty, or not resolution, but uncertainty. And then using the design uncertainty calculation, we were able to determine its design error of plus or minus 66.6 psi.
So in conclusion, the whole reason we did this project was to determine the flow rate and pressure. And with our data, we found that the flow rate was 3.6 gallons per minute, plus or minus 0.005. To put a little reference on that, that's about a tablespoon per minute uncertainty in our measurement. The flow rate we needed to reach our half a foot per second requirement was only 2.45 gallons per minute, so we exceeded that. We're happy to see that result. The maximum pressure of the hydraulic pump was found to be 2200 psi, plus or minus 66 psi. The pressure we needed to lift 500 pounds was only around 750 psi, and the pressure we needed to stay below to be safe on our hydraulic system was around 3000 psi. So that's a good point for us to operate pressure-wise.
If we were going to conduct a similar experiment in the future, here are some of the things we might consider. To reduce uncertainty in the flow rate, we'd use a more precise measurement, not from a tape measure, maybe something like a Versa gauge. That's basically like a large caliper. And we could also use a high-speed camera to increase the frame rate and a little bit of delay in between each of the frames. To reduce some uncertainty when measuring the pressure, we could use a more precise gauge. That's better than plus or minus 50 psi.
Some references are pulled equation from Khan Academy, our gauge specifications, and then our hydraulic pressure manufacturer specifications. Do we have any questions from you guys?